the door wide open.
I hope he's laughing at this all semester long. Okay, so when we say y equals the log of x, we are referring to something that is an expression you'll see in a lot of calculators called the common log. And if I go to just the built-in calculator on this device, where are we? Here you are. And this is going to be very much like every other built-in calculator you have. If you turn your iPhone calculator to the side, it becomes a scientific calculator, but not right now. And I type in, it actually kind of operates reverse. If I type in a number like 100, and I want to take the common log of that, what do you think it's going to output when I press the LOG button? It will do 2. Because a common log is a log base 10. And I want to spend just a little bit of time talking about a log base 10 because the majority of logs you're going to deal with in the scientific world when doing measurements are log base 10s. And there are 2 primary ways that we work with log base 10s. One of them I can kind of model a little bit by putting this in the middle here and then showing this with like a little thing, and then this with maybe one here, and then maybe this with one here, and this with one here. And then we'll do a big gap, and we'll do another one. And you guys realize that if you've ever done solar system scales, you'll realize that in actuality, if I start doing Pluto, I would really have to go off page here. And if I did everything else, if that was the orbit of Pluto, then the inner solar system would look like this. It'd be really, 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 really tiny. We can't really do the solar system to scale on a page. It is. What you can do is you can do the solar system on what's called a logarithmic scale. And if I want to show the kind of a graph paper that does the x in a linear scale but the y in a logarithmic scale, don't be confused for a second. Let me dissect this for a minute. This is called semi-log paper. And I want you just to look at the x-axis. The x-axis is a standard linear scale. This would be first quadrant only. But the x-axis is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The y-axis, we start to go 1, 2, 3, 4, 5. But what do you notice about the distances between 1 and 10? And then the next one, we go 10 to 20 to 30 to 40 to 50 to 60. And then the next one goes 100 to 1,000. And the next one's going to be 1,000 to 10,000. And, yep, as you get further away exponentially, you start to be able to graph things on a paper like this. This actually graphs between 0 and 1,000, but it doesn't do it in a linear scale. It does it in what's called a logarithmic scale, where the power is what matters more so than the number. If you're confused a little bit, look at the left, and what's the power of 10 right here that's just 10? And then what power is this? 2. And then what power is the last one here? So you go from 1 to 2 to 3. And the next one will be 4, and then 5. You're converting a number into its exponent, and that is precisely what a log does. A log converts a number into an exponent. So the graph of a, I'm going to kind of do this a little and let it cut in a little bit because I'm not going to have a lot of space. We're mostly going to graph this in the third quadrant. But the graph of y is equal to the log base 10 of x is a very difficult graph to actually show you. Mostly because when we do the t-chart for x and the log of x, and I put in x is 1,000, I get out 3. I put in x is 100, and I get out 2. X is 10, I get out 1. X is 1, and I get out 0. You could actually dip below the axis on that graph I showed you and go negative numbers, but they'd be 1/10 is -1, 1/100th is -2. That's actually how you graph microscopic measurements. But if I graph this on this grid, there's like maybe 3 points I can graph. This, and kind of that, but not really. 10 to the first, or 10 comma 1 would be right 10, up 1. 22 is not a point. 102 is the point, and I can't go 100 to the right. I can go 1 comma 0, and I can graph 1/10 negative 1, kind of. But that's about it. I mean, I can't really graph 1/100th negative 2. I know it gets really close. I could realize that what I'm actually talking about is this thing called a vertical, what's the word? Close, not axis, still starts with an A. It's a dotted line that a curve gets infinitely close to but never touches. Yeah, asymptote. It's a word that you guys should become familiar with. We'll deal with this more and more and more. But an asymptote is a manifestation of when you get really close to something but can never touch it. And given this curve is going to do something like this, and it will increase, but it doesn't ever increase past 2 on my graph because, well, we'd have to get 100 out to get there. This is what the graph looks like. It's just like a sharp turn, very, very sharp turn. That's the graph of the log base 10 of x. It takes a super large number, 1,000, 10,000, 1, and it changes it into whole numbers. That's a valuable function, and that's a function that in a lot of venues where you have to debate money and policy and the relationship between the two, you have to have a way for people that don't have number sense, which, let's face it, is a great portion of the world, especially the US. Sorry, Denmark, we are really falling behind on this one. Where the world, you look at the world and how they do in mathematics, and the US is like, yeah. And a lot of that, in my opinion, comes from times, and you guys might have heard of this, where you have people, parents, siblings, or something say, I just wasn't a math person, which somehow becomes an excuse for not having to understand certain things. And yet, some of the things that you guys are building here are basic, critical, essential understandings of how the world works. For one, you need to know the difference between a million, a billion, and a trillion. And not just the difference in terms of like one's bigger than the other, but what it means for one to be bigger than the other and how much bigger. And this is a way to communicate it. What's the log base 10 of 1 million? It is 6. Why? There's 6 zeros. 10 to the 6th is a million. The log base 10 of a million is 6. Think about it as its scale of number is a 6th. It's a 10 to the 6th power. What is the log base 10 of the population of the United States? We're about 330 million, I believe, somewhere in there. So we could do that. We could do that right here. 330, 000, 000. I press the log button, and I get about 8.51, 8.52.
Wait, why the first one you just have like 6 digits, 6 zeros? So that would be 6.
Mm-hmm.
This one you have 7.
Here's the reason for that. So this is a good question, Maddie. Because I know that the log base 10 of this is in between the log base 10 of 100 million. That's 10 to the 8th. And the log base 10 of 1 billion, which is 1 more 0, and that's 10 to the 9th. So given that this is somewhere in between there, 330 million is in between 100 million and 1 billion. That's where we get that 8.5. And some people say, well, wait a minute, 330 million is so much closer to 100 million than it is to 1 billion. And I will respond by, well, look at this scale here. You increment very, very greatly originally. Like think of the 100 to 1,000. Bigger gaps there, but as you get closer to 1,000, it shrinks up a little bit. That's the logarithmic scale. So back to this. That means that the scale of the population of the Earth, or not Earth, sorry, not of Earth, of the United States is about 8.52. That's like it's how big the number is on a base 10, whereas 6 seems kind of tiny. There are roughly 1 million people in the Indianapolis, like 465 boundary area. There are 330 million in the country, so you see the difference in scale. Let's jump scales to the population of the planet. So we can guesstimate that there are about 7.5 billion. When I was in college, it crossed 6 billion. The growth curve of the planet is another curve you should recognize if you saw it plotted. It is this is before millennials. The growth rate is slowing, but it's not slowing quick enough. I am on, yes, cusp. I'm dead smack in the dead center between Gen X and millennial. There's like this. You're Gen Z. There's like a wave of like a couple of years where they just don't know what to call us. Okay, hang on, guys. Let's do 7.5 billion. Okay. Log, we get 9.87, 9.88. So we'll write 9.88. That's the log base 10 of 7.5 billion. And I will get people, and you will get people that see these numbers and say, well, wait a minute, that's pretty close to that. It's pretty close to 8.5 until you realize, well, wait a minute. It takes 10.5 times one to get to the other. Like, that's not close at all. These are big gaps between them. You could even then do the log base 10 of the national deficit. Or sorry, national debt, not deficit. This is about 24 trillion. So let's do the log base 10 of 24 trillion and see about where we get 24. This is billions, millions, hundred thousands, and ones. Oh, got to do log. 13.4, or 3, 13.38, we'll say. So now we're talking about a scale of 13.38. And I think, given that you see the relationship between this is the population of Indianapolis moving to the population of the United States, moving to the population of the planet, now moving to the debt we have, or like, there's a big difference between 9.88 and 13.38 in terms of scale. Could these numbers here, the smaller ones, help you understand planetary distances and how far we are for the next planet, to the edge of the galaxy, to the next cluster or supercluster of galaxies, to the possible edge of the known universe? Like, it becomes so much more valuable to talk about numbers in terms of their logarithms than it does in terms of just the strict number itself. You don't care, and you shouldn't, whether it is 2 million miles or 3 million miles to a certain planet. You care that it's millions. Does that make sense? You want to know the scale, not the number itself. That is also true, bio people, of the microscopic world. Because in the microscopic world, you need to know, are you talking millimeters, milliliters? Are you talking micro, which is 10 to the negative 6? Are you talking nano, which is 10 to the negative 9th? Are you talking pico, 10 to the negative 12th? Are you going subatomic? In which case your numbers, your negative numbers, start getting super large because now you're talking smaller and smaller and smaller. So a logarithm in base 10, measurements like the metric system we use, they become very important in being able to characterize what multiples of 10 we're talking about. That is just the tip of the iceberg of like the, I know. Okay, back to, I want to show one more example of this, and this is kind of a day about seeing where we are going with this. We said the log of x without a base is a base 10. That is the de facto standard for what we call the common log. Yesterday, 3.14 accentuates a difference between physicists and mathematicians. Physicists love diameter. Everything with physicists is about diameter of things because that's something that you can measure. You can take an object and measure the diameter of a circle. We math people don't care about diameter of a circle. We care about radius. Everything is the measure of the center to the edge. The physicists won this fight with pi. The circumference divided by the diameter was pi, because they could measure both a diameter and a circumference and do a division and be like, whoa, neat. Mathematicians would have rather had it be 2 pi so that you could do a true ratio of the circumference to the radius. This is another case of where this is occurring. Base 10, neat. The only reason we use base 10 is, everyone, hold them up, 10 fingers. Another base you could use is this one, the LB of x. And aside from Ben being confused, because in this case, LB means log binary and not pound, log base 2 of x is called the binary log. This is rarely, if ever, used and written like LB of x, but it's a common log that you use because you do log base 2s a lot. Binary is common in programming. But I'm going to do a little bit of a gap here because neither of these are the mathematical log. They are not. They are not the log you will use in most of the calculus and pre-calculus stuff that follows. That is not a log base 10. It is not a log base 2. It is a log base. Nope. Nope.
100.
Heard it.
1,000.
It's a log base e, which of course raises the question that you're going to groan at, what is e? And let me explain e to you for a second, just in a way that you can understand what e is talking about. And we're going to do this in really quick because we're running out of time here. Many of you are going to be in a bio class your freshman year of college. If you want to do anything science related, you will be in a bio class your freshman year of college, and you will plate bacterium. The bacteria typically double. One bacteria doubles every hour. So in 1 hour, at the end of 1 hour, you get 2, right? But guess what? It's not like at 59 minutes, you have like 1, and then boom, you have 2. It's in the process of dividing throughout that hour. While it's dividing, it picks up the DNA necessary to begin dividing itself. And so you actually get something that looks like this, and then this, and then this, and you keep dividing. So at the end of the hour, you do not have 2. You have about 2.71. This is natural growth in many, many ways. Not just organisms, but if you put money into a compound interest account, this is how it grows as well. That is equal to E, and it's a number we will spend a lot of time next semester studying, and the log that it comes from is called a log natural. Well, that's why it says ln, but it's called natural log. We will spend a lot of time on natural log, so much that in college, log actually means natural log and not log base 10. For now, we just keep it base 10. Okay, say bye-bye, Ben. Bye-bye.